Hello everyone, welcome once again to my channel Orbital. This is Dr. Sushmita Yadav and we are doing the hyperconjugation. One lecture is already done on hyperconjugation in which we have discussed the condition required for hyperconjugation and we also detail about the carbocation hyperconjugation in carbocation stability. Now in this lecture we are going to discuss about the hyperconjugation in alkene and hyperconjugation in free radical system. So what are the requirements for an alkene or free radical system? It is same as the carbocation. As we learned, there must be a alpha hydrogen or presence of alpha hydrogen in the molecule will lead the stability of all these systems. So let's take the hyperconjugation in alkene. Hyperconjugation in alkene. So for example, hyperconjugation in alkene, let's suppose we are having this system. This is the alkene system. This is our alkene system. This is attached directly to a carbon which will be taken as the alpha carbon with respect to this, and this alpha is having sp3 hybridization and also having the hydrogens, which is the requirement for hyperconjugation. So let's take it like this. This is the CH3 group which is directly connected to a alkene system. How the hyperconjugation will run? Same as the carbocation, it will run. This bond will be shifted here. Sigma bond will shift it to the pi and this bond will be shifted here. So what will be the next hyperconjugated structure for this? The next structure will be this. This hydrogen will lie without bond. Two hydrogens like that, and the after bond shifting, this carbon will be negative. Same thing will happen with other two. So how many alpha hydrogen are there? Equal to that, total hyperconjugative structures are going to form here and we can have a final structures like this. This is the three structures and the fourth structure will be similar to the carbocation. It will run in the same way. Only what is the requirement? There must be a double bond system directly attached to the carbocation. So directly attached to a alpha carbon which is having the hydrogens. So these are your systems. How many hyperconjugative structure for this? It was having 3 alpha H. There was 3 alpha H. So it can form 3 hyperconjugative structures. And more the hyperconjugation means number of alpha H if increases, hyperconjugation will increase. It is a donating effect. So it will be called plus hyperconjugation. And hyperconjugation increases means stability increases. So here we can check the order of stability of alkenes in the different molecule having the hyperconjugation. Only the condition is that your alkene system must have more and more hydrogens at alpha position, or alpha carbon must have more hydrogens. More the alpha hydrogens, more will be the stability. Let's take few more examples here for the comparison. Like this is your alkene. Another alkene I am taking like CH3, CH2, double CH2, CH, double bond CH2. Yes, which of the following alkene is more stable? This is your alkene system. Okay, with respect to this is alpha carbon. So how many alpha hydrogen are there? 3 alpha hydrogens. So there will be 3 hyperconjugative structure. Now count for this. With respect to this system, this is your alkene system. With respect to this system, this is your alpha carbon and this will be considered as beta. We want hydrogen on alpha. If beta is having more, doesn't matter. But the alpha is having how many here? 2 hydrogens. That means if I draw the structure in the same pattern, I can draw 2 structures for this. Okay, so there is 2 alpha hydrogen. So here, which is more? Even though if we check the I effect of methyl is lesser than ethyl, so it is showing more plus I in comparison comparison to this, to alkene, but hyperconjugation is a more dominating effect over the inductive effect. In the last lecture, we discussed about that. So here, even though its plus side is greater, but hyperconjugation is lesser. That's why what will be the stability? Hyperconjugation, 3 hyperconjugative structure, 2 hyperconjugative structure. That means it will be more stable. Okay, let's take few more example. For example, this is an alkene. One, two, and this one is the third alkene. Just count quickly the alpha hydrogen A, B, and C. In these cases, just remember this is the thumbnail point. Now here, with respect to this alkene, this position is alpha as well as this position is alpha. So here, the alpha is having how many hydrogen? First of all, check. They should be sp3 hybridized. They are sp3. There is no sp2. So these alpha are sp3 hybridized. It is having 2 hydrogen and this one is having 1 hydrogen. So how many hydrogen? 3 alpha hydrogen. Now, with respect to this alkene, this carbon is alpha, this is alpha, as well as this one is alpha. You can count the hydrogens. There will be 3 hydrogen because it is written as CH3. 3 hydrogens, 2 hydrogens, and 2 hydrogens. Total hydrogens are how many? 3 plus 2, 5 plus 2, 7. There are 7 alpha H. Correct? So 7 hyperconjugative structure. Now in this case, with respect to this alkene, this is alpha, this one alpha, and this one is also alpha. These carbons are having 2 hydrogen. These carbons are having 3 hydrogens. So total hydrogen will be 3 plus 3, 6 plus 2, 8 plus 2, 10. So total hydrogens are 10 alpha H. So what will be the order of stability of alkene? Order of stability of alkene will be this one. Okay, more the hyperconjugation, more the number of alpha H, more will be the stability. Okay, now I am going to take a very good example of the butene, in which we will compare the hyperconjugation and learn about some exceptional behavior also for the comparison. Like we are having butene. Butene means I can draw, this is one butene. You can write it CH3, CH2, butene, all the isomers. And we will check their stability. First I can draw this, second maybe this one, and the third I can draw like this, isobutene. So the question is that what is the stability order of these 3? So we will check quickly the alpha hydrogen. With respect to this double bond, there are 2 alpha hydrogen. 2 alpha hydrogen. This is but 1 in 1 butene. Correct? 2 alpha hydrogen. Now, this is your double bond system. With respect to this, if we saw the left hand side, it is alpha hydrogen. And with respect to this is also alpha hydrogen. So how many? Total 6 alpha hydrogens are there. This is butene. Okay, and its common name is the isobutene. If you want, you can write for the IUPAC name also. That also very good. Now here, with respect to this side no alpha hydrogen, but this side we are having, this is alpha, with respect to this double bond. So here again the 6 alpha H. So the order, why it is a good example? Because you are seeing here, we know in the stability order that A is the least, but1 is the least stable. This is A, B and C. A is the least stable, but how to find out in the B and C what is the stability order? If you want to check the stability in that case, you need to check their hyperconjugative structure in detail. Okay, now I am drawing the hyperconjugative structure of these two, and you can compare their stability and can check which one is more stable among these two, because the number of alpha hydrogen in both of these are going to be same. So first I am drawing for this one. Okay, your hyperconjugative structure, this is your CH3 and CH double bond CH, and this is again CH3. So you can see clearly when this bond will be transferred, this will be transferred here. Okay, that means as a result here the carbanion will be formed, and your next hyperconjugative structure will be having this one. This is the hydrogen positive charge, and here is the double bond will come, and then this is the single bond, and this CH will take up the negative charge. This is again second side of CH3. Three structure will form in this way, and when we will run the same thing, the negative charge will go over this. I hope you are understanding what I am saying. In all these cases, what is the common thing? When we are running hyperconjugation from left side CH3, your carbanion will be formed, which is secondary in nature. Secondary carbanion. Secondary carbanion. And when we will run hyperconjugation from this side, your negative charge will come on this carbon, correct? That means, okay, I am drawing one structure from this side also. Let's see from this side. For example, it is running here. As a result, this double bond, this blue color I am showing from the right side. So here, what will be the next hyperconjugative structure? I just want to show you that where the negative charges are going in both the cases, either left hand side or either right hand side rotation. Okay, right hand side or left hand side, we are running the conjugation. So you can see, if we are running for the right hand side group, then again you are getting a carbanion which is secondary in nature, correct? Now see the same thing for this. If we are drawing the hyperconjugation for this, let's suppose this is a group, here is the CH3 double bond CH2. This is the double bond shift, pi electron shifting takes place, and the negative charge will come over that first carbon, and your next hyperconjugative structure will be this one. Have patience and check the minor details of the question. What is the nature of this carbanion? This carbanion is the primary carbanion. Okay, because the stability of these two we can't define by hyperconjugation, because hyperconjugation is equal in both. So we will check the point of difference. The point of difference is that when we are running hyperconjugation in isobutene, we are getting primary carbanion either with this 3 set or either with this 3 set of the hydrogen. We will get the primary carbanion. But in the butene case, we are getting all the time secondary carbanion, and we know the stability order of carbanion is what? Stability of carbanion. Stability of carbanion order is primary is more stable than secondary. It is just reverse of the carbocation. So which is forming more stable carbanion during the hyperconjugation? Definitely primary is more stable than secondary. So hyperconjugative structure number is same. They both will form 6 structures. But the hyperconjugative structure stability is varying in terms of the carbanion, because whenever the hydrogen donates, carbon gain electron and it become to the carbanion. So that means but2ene is more stable than the isobutene is more stable than the but2ene, because but2ene is giving you what carbanion? Secondary carbanion. And Isobutene is giving you primary carbanion. Primary carbanion means it is more stable in comparison to the butene. So what is your stability order? This will be more stable as compared to this. So your B and then C. So this is a very interesting example of butene where the hyperconjugation is same in those two. But isobutene is more stable because hyperconjugative structures are forming more stable carbanion. I hope the topic is clear to you. So this is about the simple example of alkene. Let's see few more examples and then we will see hyperconjugation in free radicals. Okay guys, let's see some more example of the hyperconjugation. Here, how many alpha H? Because these are alkene system for taking the electron. So these carbon can give the hyperconjugated pair of electron and can start the resonance with the ring. So while the methyl group or the toluene is more stabilized by resonance in comparison to the normal benzene, the reason is that the group is giving hyperconjugative stability along with the resonance. Means this group can coordinate in resonance by giving the pair of electron through hyperconjugation, because alkyl group do not have lone pair to give. So they give the pair of electron through the hyperconjugation. So how many alpha H are there? 3 alpha H. So there is 3 alpha H. It can coordinate 3 times with the benzene ring to run the resonance. Here, with respect to the ring or with respect to this double bond, this is alpha, this is beta, it is having only 2 alpha hydrogen. This one is having only 1 alpha hydrogen, because these 2 positions of methyl will be beta position, not for the use of hyperconjugation. Now, one more thing, we have learned that alkyl group is a plus I group. Yes, that's true. But that is also true that plus I stability is lesser than the hyperconjugative stability. If we check the plus I impact, plus I effect of this group is greater than this group and greater than this group. Okay, plus I is increasing in this direction, but the hyperconjugation is increasing in the reverse. And we learned already in the last lecture that hyperconjugation is more impacting or more successful effect for stability than the plus I. So which will dominate? Definitely your hyperconjugation will dominate. So whenever you are doing examples, please compare the effects nicely so that you can check it well. So here, this will be more stabilized in comparison to this, and the stability order will be A, B and C. Correct? Now here, again simple example of alkene. In the alkene, there is no alpha hydrogen because there is only the alkene. There is no further carbons to give the alpha hydrogens. Okay, so there is no hyperconjugation. In this case, with respect to your alkene system, this is your alpha and it is having 3 alpha hydrogens. Okay, now this one, with respect to this alkene system, this is alpha, total 6 alpha hydrogen. In this case, this one alpha, with respect to this side, this is also alpha. 9 alpha hydrogens, and here all the 4 positions are alpha. Mind it, always only and only alpha. If your chain is having more carbons for the next and it is having more hydrogen, they will not impact your hyperconjugation. Only the alpha position. Okay, this will be 12 alpha hydrogens. Okay, that means the stability order will be your simply A to B, or we have already learned this as a rule that more substituted alkene are more stable. This is the reason why the more substituted alkene is more stable than the less substituted one. This is due to hyperconjugation, because more substitution means more alpha positions. Correct? Now, along with this, I will discuss about reverse hyperconjugation. Reverse hyperconjugation is a special case that is found in alkene whenever alkene is connected directly. Reverse hyperconjugation. Take it like a special case of hyperconjugation, because you are seeing in all the hyperconjugation. Hyperconjugation is a plus effect, means electron donating. Always the CH electron is given to the system, whether it is carbocation, alkene or free radical. But reverse hyperconjugation, this is also called negative hyperconjugation. Means here, instead of giving to the system, it will take electron from your system. And among the carbocation, free radical and alkene, only the alkene is capable to give electron because of having pi electron system. So reverse hyperconjugation is a case found in the alkene. So here the condition is that if your alkene is directly connected to the alpha carbon who is having the highly electronegative atom. Highly electronegative atom, either fluorine or either chlorine. Only these two will work here, because these are taken as the highly electronegative. So in general, if I compare the same example with the H, what is going to happen here? There will be the alkene hyperconjugation. This will be the direction of flow of electron. But here, due to the presence of highly electronegative atom, instead of giving electron, they are going to withdraw electron. Okay, that means it will give electron here and the carbon will take up electron like this. From carbon to the chlorine. So its next structure will be something like that. This is the Cl. This Cl will present as Cl negative and the carbon will be the positive. That means here the direction of flow you can see in comparison to this. This is the hyperconjugation, means plus hyperconjugation. This is the reverse hyperconjugation, means minus hyperconjugation. So in this case you can see the direction of flow of electron is reversed to this. So this is the special case of hyperconjugation, either in chain or either in ring. If the alpha carbon is having a highly electronegative atom, like in comparison to this, like this is having 3 fluorine and this is having 3 hydrogen. So one will give the plus hyperconjugation and will increase the stability. This will give the negative hyperconjugation and will call to show the reverse hyperconjugation. So don't worry, reverse hyperconjugation will be found when your alpha position is having highly electronegative atom, either fluorine or chlorine. So this is about reverse hyperconjugation. Let's check few examples of the free radical to complete this topic. Okay. Okay, let's see hyperconjugation in free radical. We have already learned about the alkene and carbocation. In a free radical, actually the stability order follows like the carbocation, but how the hyperconjugation runs. For example, this is a free radical system. We all know that free radical means carbon is having a single unpaired electron. That is called free radical. Okay, so here how the hyperconjugation will run. In this bond there are the pair of electron, and out of the pair of electron, because to form a pi bond, this carbon need only one electron when it is already having like the free radical. So here it will give its one electron, single electron, we show by the hook arrow, means half arrow. Okay, and there are the 2 electrons in this bond. Out of that, one will be given to this side to form the bond and one will be transferred to the carbon. So what will be your next hyperconjugative structure in the free radical? The hydrogen, instead of carrying positive or negative charge, it will carry a free radical, and this will be your CH2. Correct? So likewise, it will run for all the cases. Only the thing is that here the CH bond is not donating a full pair. It is giving one electron because the carbon was already having one electron. So likewise, your hyperconjugation will run over all the hydrogens and it will give stability in the same way as it was giving to the carbocation. So this is the hyperconjugation in free radical. Rest will be the same like the carbocation. So how many alpha H are there? 3 alpha H are there. So 3 hyperconjugative structures will be there, and more the hyperconjugative structure, more will be the stability. So you will check in the same way as you were checking in your Normal examples, this is a free radical. Okay, I am writing like CH2, free radical. Here, your free radical is present here. Here, your free radical is present here. So just check what is the stability order. Only you need to check the alpha hydrogen. So with respect to this is alpha location carrying one hydrogen. So there is one alpha hydrogen. Here, this is one alpha, another alpha, this is third alpha. So 2 hydrogen at these locations, this is 3. So 3 plus 2, 5 plus 2, 7 alpha hydrogen. This one is having, this is alpha, this side 2, this side 1. So there are 3 alpha hydrogen, rest is same. So the order of stability will be, if I concern with take it like A, B and C, order of stability will be B is more stable than C than A. Okay? So it will run in the same way, only the difference is that instead of donating full pair of the sigma bond, it will give only one electron, because to form a bond only 2 electrons are required and 1 electron is already present on the carbon. So it will take only 1 electron from hydrogen and rest will be transferred to the hydrogen to form the another free radical hyperconjugative structure. Stability you can count in the same way as you were counting in alkene and carbocation. Count the alpha hydrogen and form the order. So this is all about the carbocation, hyperconjugation and alkene and free radical hyperconjugation stability. I hope the video will be useful for you. Keep watching and keep supporting me. Thank you.